This will be Mujin's first talk at IBS. We talk about induced minors, letter, wheel, stars. Yeah, please.
Okay, thank you for coming my talk. So I'm very nervous, so maybe I talk too fast. Please slow me down and please interrupt me anytime you want. So today I will talk about excluding letter and wheel as an induced minor in graph with a large stars as an induced graph. This is based on two papers. First one was accepted on WG. This year it's based on work with Claire Hilaire, who's in France now, Milanič, who's professor in University of Primorska, and Sebastian Wiederrecht, who's there. And second paper is with Sebastian. Okay. So we love graphs. Especially we love simple looking graphs. So the trees are really basic kind of graphs that even like many hard problems become easier on trees. So one good thing about tree is when we delete one edge or one vertex, tree will just disconnect to many components, then will never interact with each other again. So for similar reason, we like graphs looks like a trees. So these kind of graphs are called graphs with bounded tree width, and it's been studied like with thousands of papers for last decades. So I will explain more about these tree widths. So here is one example of tree decomposition. I intentionally brought a graph that doesn't look like tree. Here, a Peterson graph. So a tree decomposition of a graph, here is a graph, is a tree where each node of tree is assigned with some set of vertices. But it's not just a random assignment. We have to follow three rules. First, for each vertex in the original graph, there must be a node that contains that vertex. Second, for each edge in the original graph, there must be a node that contains the both vertex instead of that edge. Last one, for each vertex in the graph, original graph, the nodes that contains that vertex should be connected in our tree. So that's three conditions we have to satisfy. The tree width is defined as before that, the width of this tree decomposition is defined as the maximum size of one bag minus one. And tree width is defined as the minimum width over all tree decompositions of a graph. Here, this one shows this tree decomposition has width 4 because the bag with maximum size has 5 vertices in it, and it's optimal. So giving that Peterson graph has tree width 4. Okay, so what is good with tree width? It has many strong algorithmic applications, but in this talk I will usually concentrate on structural properties. In the core of the power of tree width, there lies a great theorem by Robertson and Seymour. They say that if graph has large tree width, it will have a k by k grid as a minor. Okay, and for a long time, people tried to make these grid theorem like theorems, and people tried to find the induced version of grid theorem. So people was asking the problem like, can we find some certain condition such that every graph with satisfies this condition contains the k by k grid as an induced minor. So I will explain what is induced minor. In the graph minor operation, we allow three operations. First, vertex deletion. So here we remove this red vertex and delete all the incident edges. Second, edge deletion. Here we can just remove this blue edge. And last, edge contraction, which is you can think that we can make this length of this blue edge by 0 and merging the two vertex in both ends. In induced minor, we do not allow edge deletion and just allow vertex deletion and edge contraction. You can think as the relation between subgraph and induced subgraph. It's the same relation holds between like minor and induced minor. So people was thinking about this induced version of grid theorem, and Cronin proved that for graphs with bounded maximum degree, we can find we can find this induced version of grid theorem, saying that if graph has bounded degree and large tree width, then it will have k by k grid as an induced minor. And we wanted to generalize this theorem. Especially we wanted to generalize this maximum degree part. So how shall we do that? So beyond the maximum degree, we will think about something like induced degree. So I will explain what it means. So when we bound maximum degree, it is same as forbidding a large star, this means K1D, as a subgraph. So for example, if we forbid K16 as subgraph, each vertex has maximum degree 5. So since we are thinking about the induced version of this grid theorem, it seems it is natural to consider this forbidding K1D as an induced subgraph, not subgraph. So for example, here we forbid K14, then each vertex, its neighbor will have like at most independence number 3. So this kind of a number of vertex, changing the number of vertex to independence number will, this tactic we will use again and again. So I will explain what is the critical difference between bounding maximum degree and forbidding K1D as induced subgraph. So here is one example. Okay. So when we bound maximum degree, we have control over any distance. This means that let's say we have maximum degree 4 here. So here is the central vertex, and we look at first neighbor. It has at most 4 vertices. Second neighbor, we have at most 12 vertices because 4 times 3 is 12, and third neighbor 36, and so on. This means that when we forbid the first neighbor, then it will give control over any distance. However, this is not true for K1D freeness. So look at this example. Here we have a large clique and add a matching to each vertex on a clique. And if you look at this graph, this one is K13 free. So this vertex, looking at this vertex, its neighbor has independence number 2, but its second neighbor has unbounded independence number. So we lose the control over long distance. Here is one thing we also should care, is that when we forbid K1D as induced subgraph, then it means that we will allow all the large cliques in our graph class. So since this large clique has large tree width and K12 free, but has no 2x2 grid as an induced minor, we have to think about a tree width that somehow allows this large clique. So here comes the tree independence number. So when we looked at the definition of tree width, we cared about the number of vertices in each bed. In tree independence number, we look at the independence number of each bag instead of its size. So this was defined independently by Yolov and later by Hilaire, Milanič, and Strugel. So to elaborate the definition, so we look at the tree decomposition, and the alpha width of the tree decomposition is the maximum independence number of all its bags. And the tree independence number of a graph is the minimum alpha width over all tree decompositions. So here is an example of graph with large tree width but has small tree independence number. You can see that some part of these trees has very dense subgraph. So this makes trees large, but it is very dense enough to maintain the independence number to be small. So you can think that this is some kind of dense counterpart for this tree width. So we somehow allow large cliques while maintaining the graphs to look like a tree. Okay, so for the power of tree width, the grid theorem lies in the center, and here is the conjecture for grid theorem for tree independence number. It was conjectured by the paper by Dollar, Kwon and Crunch and Milanič, Murano and Strogel and Wiederrecht. So the sorry for bad pronunciation. I'm not sure whether I properly pronounced them, but sorry. So if let's say K1D3 graph has large tree independence number, it will contain K by K grid as an induced minor.
So when you say free, then there's no induced subgraph.
Yeah, always K1D3 is no K1D as the induced subgraph. Okay. So this conjecture is still widely open, and there are like several small planar graphs that somehow gives evidence to our ultimate goal of grid. So in the same paper, they made a conjecture. They proved that we can either find this tripod or this line graph of this tripod as an induced subgraph. And later, Maria Chudnovsky, Stefan Hajevi, and Nicola Turchinyan showed that if we forbid this theta and prism as induced subgraph, we will have boundary tree independence number. And also, Jong-Wan, Pascal Goulin, Tonian, and Ojong Kwon showed that we can also find this disjoint union of cycles. Our results gives that we can find we can find both large field and this ladder as an induced minor. In fact, we proved something a bit stronger. We can find one subdivision of, a graph that's obtained by subdividing one for these vertical edges in ladder. So I will explain why these two graphs are important. So for real graphs, this is the first graph class that is arbitrarily large and three connective, and because finding grid is same as finding wall, which is three connective, so somehow three connective is what we have to aim and what we can expect. And also you can see that this is the first floor of this grid. Okay. And also we show that using our method we can generalize this theta and prism later. Later I will explain more. Okay. Any questions until now? Great. So here are our main theorems. You don't have to read these. It's quite long and formal. But I have to mention that here the function here is not a good one. It's like quadratic exponential. We didn't try to optimize this function. And also for view, here is the function, and maybe you can guess that we used the coherence grid theorem somehow. But we improved this function in really a lot. I will also explain it later. Okay, here I will try to sketch the proof with a lot of details. Okay, here first to find ladder, we will find ladder-like graphs. It's some graphs that looks like ladder that somehow contains our ladder graph as an induced minor. So our strategy is find these two purple paths, which are non-adjacent and induced paths, and between its neighbors, we will find many non-adjacent paths between them. And
by non-adjacent, you mean they are induced paths, and between them there's no edges.
yes, this is gray area may overlap. So these paths may have like 0.
But between two paths, you don't have any edges.
This one and this one? Yes. Okay. When we look at this gray, one of these neighbor of purple paths, these non-adjacent paths may have like chaotic neighbors in this purple area. But because we are in K1D3 graphs, each this endpoint of this path may have at most 2D minus 2 neighbors in purple paths. So if there is a lot of such non-adjacent paths, we can clean up, like maybe just removing some paths this black path here and cut off this purple path a little bit. And we can do same thing on the below side. And we will somehow clean up these neighborhoods. And we can use Ehrlich-Stecker's theorem, meaning that when looking at this number, like assigning number 1 to like n, and like this gives some permutation here, and we can find some well ordered paths between these gray areas. Okay, so this one contains the letter as induced minor, so we will find this graph as induced graph. One thing note that, as I said, these paths may have length 0. We don't know how to make it longer. Okay, so to explain how to find this purple path, I have to explain the bramble for tree independence number. So the power of tree is somehow comes from the fact that it has many dual objects like bramble, tangle, welding set, cup set, rubber, etc. And we try to define the bramble for tree independence number. So here is a graph. A strong bramble is a collection of vertex sets such that each one intersects with each other. So for example, this pink one intersects with this green one here, like green and like sky blue one intersects here, etc. For normal tree width, we use for like we allow the bramble to touch each other. This means that we allow that the two bramble may not intersect, but there may be one edge that has one endpoint in one bramble element and one in the other. But here, for technical reason, we only consider this strong bramble. And a heating set for a strong bramble is a vertex that meets with all bramble elements. Okay, for bramble tree with duality, we look at the size of this heating set. And because we are looking at the tree independence number, we will again use this independence number instead of size. So the alpha order of this bramble is defined as the minimum independence number among all its heating sets. So here is the approximation duality between alpha order of the strong bramble and tree independence number. We show that if graph has strong bramble of large alpha order, then the tree independence number should be also large. And on the other hand, if the tree independence number is very large, this graph has large strong bramble.
Can you remind the alpha order of a strong bramble again?
So alpha order of the strong bramble is the maximum independence number among all its heating sets. So, any questions?
Minimum, you said maximum.
Minimum, sorry. Okay, so similar results was proven in like PhD thesis in Isozalder in much broader sense, but for more well organized proof, please look at our field paper, and I will explain a bit. Okay, so this tactic of looking at independence number instead of size of set, we will use it almost. We will use this tactic to change the approximation duality between bramble and trees. So suppose that a graph has strong bramble of large alpha order, and suppose that it has small tree independence number. Let's say this is a tree decomposition giving this small tree independence number, and look at one edge. So if we look at this back and this back, its intersection makes this separation between here and here. And because it has small tree independence number, it has a small independence number. This means that this cannot be a heating set for a strong bramble. So there must be a bramble element that does not meet with this intersection. And if there is one more bramble here, we cannot have one here because this one must intersect with all other bramble elements. So we can make an arrow on this edge. By same way, we can arrow all the edges. Then we can find the sink here. And this is the hitting set for all the bramble elements. And because the 3D composition has small alpha base, this has small independence number, which is contradiction.
Here you didn't use the strong property of the bramble, right? If it's any bramble, does it
So for
this direction?
this one, I don't think we use strong is here. I think so. Okay. So next step, we will use the balance separator and welding set, the independence number version of balance separator and welding set to prove the other direction. So suppose that here is a set X, and alpha balance separator for X is this blue set that somehow breaks this X into like in balanced manner. Means that this for each component, the independence number is at most the half of this original independence number. Also, a graph is K alpha linked. I will just say it's well linked. Say if there is no balance separator. So for any like set with small independence number, it may break graph into several parts, but one part must have super large independence number. And suppose that graph has a large K alpha link set. We will look at all these sets with small independence number, and for each one there must be a large component after deleting this that has large independence number. And if we gather all of them, we will have a strong bramble with large alpha order. Why? Because if there is
Can you go back to the definition of alpha
this one?
balanced separators?
Yeah.
Every component. Right. Thank you.
So back to the proof. Let's say if there is a hitting set with small independence number, the hitting set must be some of these blue sets, right? So we have to find one bramble element that does not meet with this hitting set, which is contradiction. So this gives a strong bramble with large alpha order. Okay, and on the other hand, we can show that if graph does not contain a large well alpha linked set, then the dependence number shall be small. So this can be proven by making a 3D conversion with small alpha widths by inductively. Let's say we start from whole graph here and choose some set with small independence number and make it as a node here and look at this intersection. So this intersection cannot be a K alpha link set. So there must be a one set that has small independence number and separates this red set. And we can make a 3D conversion like this. This means that here the middle node contains this one set with small independence number here, one set with small 3 independence number here. So we have some spare independence number to put one more vertex here, and make the remaining part as a leaf. Then we can inductively increase the number of these vertices that is contained in a bag with small independence number. And in finite step, we can construct the desired 3D conversion. Okay, is it okay? Okay.
Will this give an approximate pre-decomposition of bounded independence number? I mean, I'm just wondering, so computing tree independent, optimum tree independence number pre-decomposition is
NPR.
Yeah,
NPR.
it's also W1 hat parameterized by the.
There is like approximation algorithm that approximates the tree independence number, but I don't think they use this method.
But that's FPT or is that XP?
It needs to be XP. So in this paper where they prove this, where they provide this algorithm, they prove that finding even approximate a balanced separator of small alpha is W1.
Yeah, I think that was my question. So this approach that you're using, it does not give an FPT approximation
No.
because you can't find the.
The separator.
This separator.
Okay.
Okay, and more questions? Any more questions? Then I will start next part. We will find the we will find the path, induced path whose neighbor needs all these bramble elements, meaning that this neighbor, a close neighbor of this strong path that is hitting set of our strong bramble. So from now on, we will let's say no, not now. For now, just this general graph. So this is the induced version of method used by Bruce Reed. So I will give a proof. So here is, let's say here is our bramble elements, and we start from a path with length 0 here. We look at its neighbor, maybe it does not deal with all the bramble elements, and we will extend this path inductively. So say that in some step we have this path, this neighbor, it meets with some bramble element, but it may not meet with all the bramble elements. But because these bramble elements are always intersect each other, we can find a path from here, inside this bramble element. So our path has grown longer and meets with more bramble elements. And we can maintain that this has to be induced in this process. Okay, how to use this path? First, we have to break this path into two pieces, such that between these close neighbors of these two paths, any separator between them has large independence number. I will show how. So let's say we are in like K1D free graph with large tree independence number, then we can find a strong bramble with large alpha order and a path whose close neighbor meets all the bramble elements. Look at the first vertex here. Look at the first vertex here, its neighbor, it may meet some bramble elements, but cannot meet all of them. Because we are in K1D free graphs, so its neighborhood has independence number and more, less than D, so it cannot be hitting set of all bramble elements. If we extend this path by one vertex, it has now a little bit larger independence number, but the independence number of this neighbor cannot be like increased a lot. Because we are in K1D graphs, so this independence number of this neighbor increased and mostly each time. So we repeat, and at some step, there should be some time that our path, its neighbor has like lots of bramble elements, and it still have lots of bramble elements that does not meet with this neighbor. I mean, when I say meet a lot and does not meet a lot, it means that alpha order of these brambles here is large, and also alpha order of this bramble our path did not meet is also large. Okay, then we delete the next vertex here and shatter the path into two pieces. These are the purple paths that we tried to find in the first. So I will show that for any separator between them has large independence number. And suppose not. Then because it has small independence number, it cannot be hitting set for the bramble elements where this first path did not meet. Same for the second path. And here, because bramble elements always intersect each other, we can find the path from here to here, which is contradiction. So any separator should have large independence number. And somehow we want to say that there are many normalization paths between here and here by using some Menger-like property, but unfortunately this is not possible. So here are induced Menger conjecture. There's a lot of versions of induced Menger conjecture, which a lot of them were disproved. But I hope that these versions survive for a while. Anyway, this I want to say that for any set of vertices, either there are k-pairized non-adjacent paths or any separator between them has small independence number. We don't know this conjecture, but one fortunate thing is we do not need full power of Menger's theorem. So we want to find fixed graph as an induced minor. This means that we don't need these two sets to be arbitrary. We can just say these two sets are given. And furthermore, we may say that they may change in the course of proof. So that's what we will do. So instead of building a ladder like this, we will find a new path here and make a ladder between these paths and the first one. Okay, how should I do that? So here are the two paths such that between its neighbors, it has any separator between them has large independence number. And let's say if there is many non-adjacent paths, we found a ladder here. So we may assume that there is only bounded number of them. And we remove two vertices from both sides of these paths and its neighbors, and just remove them. We will never interact with these red sets here. What's good with this? By removing them, we can guarantee that the surviving neighbor of these paths and the surviving neighbor of this original path, this gray area, does not intersect. I had to say that when we find these non-adjacent paths, we have to be greedily find shortest paths in each step. So then we can guarantee that this blue area and gray area does not intersect. And then we can do one more step. Here, from this blue area to above gray area, we can find many non-adjacent paths. Suppose that we find too many, then at least one of these blue area should have large this paths between gray and blue. This gives ladder here between this and this. So there must be bounded number. Okay?
So can you say again what you still want induced paths?
Sure.
So why are these paths induced?
So to say that we can find at least one such induced path.
Just one.
Yes, we have to use the property that this red area cannot be the separator between here and here, and a bit more. I will just skip the detail. So we again exclude these two endpoints from both sides of test. Then we find non-adjacent paths between this green and gray area. Remove these two vertices from both ends again and again. Then if we repeat this process too much, we can find the ladder here. So these rail paths here can be found like from here by using these paths from each step a little bit, and we can find the path between these purple paths using these the other parts of our non-adjacent paths. This gives our ladder. Okay, any questions until now? Okay, so I will go to the wheel. I said that in the wheel paper, our wheel paper, we originally used the coordinates theorem and gave a bound using that theorem, that function, that theorem. But we improved this function a lot. It's almost just k times d. So I will explain how. So let's go back to the time when we break the path into two parts. First, we want to shrink this path a little bit, such that this is the minimal path that meets all, whose neighbor meets all the bramble elements it previously met. Then, because this path is minimal, there must be a bramble element here that is adjacent with only this vertex. Another bramble element here that's adjacent with only this vertex. And because the bramble elements always intersect, we can find a path from here to here using the inside of bramble elements. Then we have made a cycle, and we can say that this cycle is induced cycle, and this cycle is not adjacent with the another path here. And we can show that by using the similar way, we can show that any separator between this cycle and path has large independence number. Okay, then let's look at this component K of this G minus C. So if this component is component that contains these paths after we removing this cycle, and look at the neighbor of this cycle and intersection with this component K. This is the separator between this neighbor of this cycle and neighbor of this path, which means that this has a large independence number. So then we contract this K into one, before that, because this blue area has large independence number, and we were in K1D free graphs, the number of vertices on this cycle that has neighbor on this blue area must be large. Then, when we contract this component into one vertex, this vertex meets a lot of vertices in our cycle, which gives a large field.
Wait, so the previous slide you said the number of vertices on C having neighbors to K
Yes?
is small?
No, it's large. It must be large because this independence number here is large, K1D free. So for each vertex here, its neighbor has small independence number. So
okay,
their number should be large. So this gives our view. Any question until now? If not, okay, let's look at some applications. So, Marichnowsky, Sekor-Hajevi, and Nicola also showed that for any positive integer d, when we forbid K1D and these two graphs as induced subgraph, then we have bounded tree independence number. We generalize this theorem so that we may guarantee that these paths between here and here should be low. So this is one application. So the way to prove this is not first we go back to this graph here. Okay. So in this graph, we did not use the fact that these and these are induced paths. These two can be any subgraph, and we can do similar argument finding non-adjacent paths here between these two areas built like this. So we can make this cycle. We can put the cycle and path here. The one drawback is that we cannot do the cleanup process in the cycle, because if we remove some part of cycle, it's not a cycle now. So it's not very very pretty, but it's with some case distinctions, some like case distinctions with 3 pages, we can prove this. I will not explain it here. Okay, another thing is this independence Ehrlich-Poisson property. So for any induced subgraph, connected induced subgraph of this ladder, we can make this Ehrlich-Poisson like property, saying that we can find like many number of disjoint copies of this subgraph, or we can find a vertex set that has small independence number, and when we delete this vertex set, then there is no H in the H remaining in our graph.
This is only for ladders, not for wheels.
Well, I think it's also true for wheels, but okay, this is also true for wheels. Yeah, the proof of this is using the well, how should I say, some ordinary POSA kind of proofs. Again, using the tree decomposition with like a small tree independence number, or we have a large tree independence number and have a longer ladder, and we can find many H's in this longer ladder. So by saying this, I'm now I have to say that for wheel this not holds, because large wheel does not contain a lot of small wheels in it. I need that.
But I guess any induced minor of the wheel that's not a wheel is contained in the ladder, right?
Yes, that's also true. Ah, yeah, that's right. So, okay, so here are possible next steps toward our induced grid theorem. First one, double ladder and double wheel. That's well, we can look at the second floor of our grid-like graph. But there's one problem here. As I said before, we used our method. It is hard to say how this test is connected to this ladder here. So they can be connected, all of these tests, I mean, between this test and this ladder, we can say that there are many non-adjacent tests, but they may attach to this ladder in like very chaotic way, and we cannot clean it up. And similar thing goes for our double wheel. Another question we can ask is, instead of K1D freeness, can we ask KDD free? Because another goal can be, can we imitate more theorems for tree with tree independence number? It's a well bigger question to pursue, even after we find grid theorem. Okay, thank you for listening.
Alright, any questions?
In your main theorem,
Yes.
is it also possible to really find such an induced minor efficiently?
Yes. Well, efficiently. No. I will explain why. So, the critical step that makes our the algorithm version bad is finding the alpha bramble. Except that everything is, I think everything is can be done in like FPT time, but for finding alpha bramble, I don't know. It must need exponential time. Okay. So
So I guess there are alpha tangles as well. Like if you just
yes, you can.
if you
also-
measure the order by just the independence
Yes.
number, it's, you should have a duality as well.
I think so.
You can define it. The problem is you don't get as nice of theorems as in the normal tangle sense, because using alpha as the measure of your separations is not submodular. So most of the arguments usually done in tangle theory just break down. You can define it, you can prove an approximate duality using these arguments, but you can't do better.
Yep.
So K1D free is like restricting the alpha value of the neighborhood, right?
Yes,
So
that's right.
you're restricting to a graph class where alpha of any neighborhood is small, and then try to prove something.
Yes.
So is this function alpha special? Like if I replace alpha by a different function on the vertex set of the graph, is there any chance that similar proof may go through? Like instead of
Ah.
alpha,
I think
choose the like
there-
weighted
it seems like we have
something
to
or any function behave like satisfy certain actions.
okay, we have maybe I think we have to check two things. First one is there the bramble duality for that function? I mean, it depends on the some properties of that function, maybe some submodularity or like how the addition works in that function, something like that. And second thing, give me a second. Okay, I think the second thing was the what I already said, the how they act when we take a union of disjoint such sets.
And so maybe you can extract like what kind of axioms you want from the from your function.
Yes, I think that's possible.
I can say something if you want.
Yes.
So there's
Please.
Isolde has done something like this in her thesis, at least for bramble duality.
Uh-huh.
So there's a small set, and we do something similar. So there's a small set of axiom you can impose,
Uh-huh.
and for certain types of parameters this works. It fails for others. You need some sort of non-local property. So things like dominating set completely don't work.
Uh-huh.
You can't use it. But things like click cover, for example, perfectly fits into this this thing.
I see.
In particular, you need, if you have two disjoint and non-adjacent sets, then the values of both sets together should be the value of the union of the two sets. So if you just take value here plus value here, it should be the same as value of the union of the
I
sets.
see.
That's really important.
Uh-huh.
Any more questions? Then thank you.